Okay, let's get started. Everyone, good morning. Topics for today, we're going to wrap up the IP header. We had two little topics left to cover there and start on reliability. This is the topic for your second project. So we're going to get started on that today and then continue it after the midterm. So on the question of designing IP, two topics that were remaining. One was we wanted to take a brief peek at IPv6, really through the lens of what's changed, what's different going from IPv4 to IPv6. And then spend a little bit of time again talking about the security implications of the IP header. And so jumping straight into IPv6, I think Murphy touched on this a little bit in his lecture on addressing, but just to recap, roughly about the late 90s, people started panicking that with 32-bit IPv4 addresses, we're going to run out of address space fairly quickly. And so IPv6 was an effort that started, it was motivated by this concern about address exhaustion. And so IPv6 goes all the way to the other extreme. Addresses are 128 bits long, so they have 4 times more bits than in IPv4. So it seems very likely at this point that we're never going to run out of addresses using IPv6. Where is IPv6? It has been a slow process of deployment. At this point in time, I would say, I think depending on which numbers you believe, between 30 to 40% of the internet is using IPv6. But, there have been major announcements. For example, all of China has said that they're moving to IPv6. All of the major cloud providers support IPv6. So at this point in time, there's no question that IPv6 will one day be the version of IP running on the internet. It's just a question of how much time it's going to take to get deployed. While IPv6 was primarily motivated by this concern about we need more address space, we've run out of addresses to allocate, the designers of IPv6 also took the opportunity to do a little bit of a cleanup on the IPv4 header. So we've talked as we went through the IPv4 header about why do we have this field. This field looks complicated. Operators don't really turn on this other field and so on. So they did a little bit of, let's call it spring cleaning on the IPv4 header when going from IPv4 to IPv6. That's about the extent to which the designers tried to effect change, going from v4 to v6. So, for example, some of the things they did not touch or did not address were things like security and concerns about IP address integrity and so on, which we'll touch on. So overall, I would say IPv6 is a nicely designed. It's an elegant protocol, and the changes they made make sense and are nicely done. It's not a particularly ambitious protocol. So everything we've learned about IPv4 still applies to IPv6 with a few changes to the IP header that we'll talk about. Okay. So with that, here's the IPv4 header. We talked about it last time. If you need a reminder, there are a few fields up there, versions, header lengths, and so on, that were for parsing. There's a source and destination address, of course. Then there are a few fields to deal with issues like fragmentation, looping, checksums if packets get corrupted. And then there were a few fields in there to deal with what if you wanted exception processing, so type of service or this notion of options, where you can ask for advanced functionality. So if you were doing IPv6, what cleanup would you do? We're going to increase the size of the addresses, so let's take that as a given. But what else would you clean up, change, do differently? Yeah. Remove the checksum. Anything else that can go? Or that you don't like, you would do differently? You don't have to know how to fix it, just things that didn't please you about the v4 header. Okay, we'll take the checksum. Let's start with that. So summary of changes, we expanded addresses. We eliminated the checksum. Why did we eliminate the checksum? Because as we discussed in class, you could have just let a corrupted packet go all the way to the receiver and have the receiver check whether the checksum was correct. And if it wasn't, it could drop it. Right. So strictly speaking, we didn't have to have every router recomputing and checking the checksum. The only thing you wasted by having the corrupted packet go all the way to the receiver was a little bit of extra bandwidth along the path. Okay. So that's why we eliminated the checksum. I'm going to tell you that IPv6, for fairly similar reasoning, eliminated fragmentation. You've now done fragmentation in section. So how would you deal with a packet that is larger than the MTU if you didn't have fragmentation support at routers? The end host could, which end host? You're on the right track. The sender. How would the sender know that it has to fragment? Yeah? Yeah, so that's exactly what IPv6 does. So in IPv6, the way this works is if the sender sends a packet that is larger than the link MTU, that packet is going to make its way through the network until it reaches the link where the MTU is smaller than the packet size. That router is going to drop the packet and send an error message back to the sender saying, you need to send smaller packets, this is my MTU. And then the sender is going to actually send out packets that are the correct size. So again, trying to push work off to the end host. Did that make sense to everyone? The other thing that IPv6 changes is the options, how options are handled. So if you remember when we talked about options, we said, well, because you have options, the header length is variable, which means you typically have more complicated processing at the router. Rob was saying how typically at Google, for example, they don't even treat options. They ignore them or they drop packets that have options. So options in general have been a little bit of a troublesome thing in the IPv4 header. And so the way IPv6 addresses this is it kind of says options are not part of the IPv6 header, but it gives you a mechanism by which you can still have options somewhere else. And the way it does that is actually pretty clever. If you remember going back to the IPv4 header, we had this protocol field, which we said we are going to use to tell the end host what is the layer 4 protocol you're going to have. And we said they're well-known protocol numbers. So for example, if you said my protocol field is 6, that was telling the receiver that your next header is a TCP header. Okay? So in IPv6, this protocol field is now called a next header field. And it still does the original job. So if your next header field says 6, that tells the receiver that your next header is TCP. But in addition, what IPv6 says is that you could, if you wanted to have options, so let's say, for example, you wanted to do source routing as an option, then the way you do that is you go define a source routing header. You go to the standards body and you say, I need an option for source routing. This is what my source routing header is going to look like. And you get the equivalent of a protocol number that tells the router that your next header is a source routing header. And so now if you want to have options, the only thing you have to do in the IPv6 header is that you say that your next header field is a source routing header. And then when the router can go look at the source routing header, and in the source routing header, the next header field would tell you that the header inside one level is TCP. And you could continue to do that. You can start to chain these options. So you could have an IPv6 header that's pointing to something like a source routing header. The source routing header, this is another type of header, could be an authentication header where you're checking that this is a valid packet. And ultimately, talking to the next header would be a TCP header. Okay? So the way to think about it is options have gone from the IPv6 header. The IPv6 header doesn't need to know about options. But there's this way of squeezing them in between the IPv6 header and the layer 4, the TCP header. Okay? Any questions on that? Yep.
So wouldn't the fragmentation mechanism slow down the entire network? It keeps on having to set it over and over again until it's the right size.
So going back to the fragmentation question, great question. What if I had an MTU on let's say the source was initially sending 1,000 byte packets, and there's an MTU, a link that has an MTU of, say, 500 bytes. And then after that, there's a link that has an MTU of 250 bytes. So you're right. In that case, what would happen is you would send a 1,000 byte packet, you would get back an error message saying you have to send something less than 500. If you then send 499, it's going to go to the next link, which will send you another error message. So yes, you're right. That could happen, and it would happen once along the path until the source learns it. The reason no one's too worried about that is at this point everyone is kind of settled. It's not official, but everyone kind of agrees that the Ethernet MTU is the MTU of the internet, so 1,500 bytes. So you'd have to be doing something pretty unusual to do that. Any other? Yeah? So a good question. Can your next header field be empty? What would that mean? So your packet would make it, every router would say, okay, there's no option, but it would make it all the way down to the destination. at the destination, I still need to know whether to hand it to TCP or UDP or some other protocol. So it'll still play the field. At the very least, the next header is the same as the protocol field in IPv4. It can be more than that, but never less than that. Any other questions? Okay. So that was the options field. The other change it makes is in IPv6, there is no header length field. This kind of follows. Why is that? Yeah. Right. The only reason we needed it in IPv4 was because of this options thing that could be variable length. We got rid of options from the IPv6 header, so we don't need a header length anymore. And then the one thing that IPv6 adds is this notion of a flow label. We haven't fully covered the context to explain a flow label, but let me try and we'll come back to it later. So the reason we have a flow label is, remember we said earlier that often when you look at a source and destination, it's not just a stream of independent packets going back and forth between them. At some higher level or application level, there's a stream of packets that are related to what the application is trying to do. For example, you could have multiple packets coming in for one download. Or in a web browser session, you could actually have multiple flows and multiple connections and multiple packets that are all part of that user's experience or the user's session. And often in the internet, there are these things called middle boxes, like firewalls or censorship boxes or intrusion detection boxes. We're going to talk about them later in the semester. But these are boxes that, for example, think of an appliance, a middle box that's trying to censor certain traffic. What it's going to try to do is to collect a set of packets that are all related and look inside that packet to say, is this connection going someplace where I don't want my users to go? And then it's going to filter. And so the network, when you're talking about these kinds of functions, it needs to have some notion of which packets together form some application context or stream of related packets that that box wants to look at. With the IPv4 header, there's no explicit way for the network to know, this sequence of packets are all related. And so instead, what we've always relied on with IPv4 is all these ad hoc rules that say, well, for all traffic going from the same source IP to the same destination with the same port numbers, these must all be related. And it's pretty ad hoc, and sometimes it goes wrong, but that's what people do. So what IPv6 instead said, okay, if there are boxes in the network that need to know which packets are kind of related, let me have this notion of a flow label. And at the end host, I'm going to use the same flow label to denote a stream of packets that are all related. So it's just taking the guesswork out for the network. Does that make sense? So for example, you might use the same flow label for all packets that are part of the same file download. You could also use the same flow label for all packets that are part of one browsing session. So both the ads and the content and the video that are part of one browsing session. There are no rules that limit end hosts on how they use the flow label. But it's a hint to the network that the end host thinks of these packets as related. Yep. As far as I know, it's up to let me double check on that. I believe it's undefined or unlimited. There might be some that are well set aside, but let me confirm that. I don't know if you guys know. No. Let me get back to you on that. Any questions about this? Okay. So IPv4 and IPv6, where does that lead us? This is the IPv6 header. So that you can compare it, here's the IPv4 header side by side. And here's the color coding. So let's go through these one at a time. Yellows are the fields that are identical, semantic and not syntactic, but semantically from IPv4 to IPv6. It's pretty much the version number. It's now value 6, but it's the same field. And the source and destination addresses. Okay, and as you can see, they're 4 times larger. Orange are all the fields that went away from the IPv4 header. So we have fragmentation, header length, checksum, and options. Okay, these are gone. Blues are fields that have they've stayed. We've either renamed them or slightly changed how we use them. So type of service is now called traffic class. Payload length we still need because the payload of a packet can still be different, right, from one packet to another. Next header is playing the role of the protocol field and more. And time to live was renamed hop limit as being, people thought time to live was not quite capturing what the TTL was doing. It's actually a limit on the number of hops. So it's now called hop limit. So that's really the extent of the change going from V4 to V6. Any questions? Yeah. So it's nice to think about actually what is the philosophy underlying all of these changes. What would you say the designers of IPv6, what principle have they been applying in doing this cleanup? Yeah. Yeah, it's a very aggressive use of or application of the end-to-end principle. Anything that could be pushed to the end host has been pushed to the end host. Right? So fragmentation and checksum are gone. In fact, the only thing that's left is the TTL. Why keep the TTL? Is that something? Yep. Yeah, because we needed TTL because of all these routing convergence issues and loops. It's really hard to imagine how an end host could help with that. Routing convergence truly is a network problem. There's also an emphasis on simplification, which is why they got rid of options and the IP header length. But at the same time, I think the thing that's nice about the IPv6 header is they've kept in mind this need for extensibility. And they've done it actually very cleanly with just this kind of generalized next header approach, which allows you to, over time, define new functions for the network, as well as this notion of a general flow label, which is, the purists of IPv4 had this idea that you have a very strict division between what the network does and the end hosts do, and the network should never look at anything more than the IPv4 header. Well, 25 years of experience has taught us that the network is looking at more than the IPv4 header. And so having a flow label is a nice way for end hosts to start communicating some of the application semantics into the network without actually embedding application logic into the network. So it's a useful way of passing hints between the end host and the network. Yeah? Yeah, so let me give you a specific example, and we'll come back to this in a much, much later lecture when we do middle boxes. But as an example, let's say that you had an intrusion detection system that's sitting in your network, that's run by your ISP. And what the intrusion detection system does is it looks at the URL that you're going to when you're browsing. And it either says, for whatever reason, parental control, I'm going to drop this traffic, or, censorship, I'm going to drop this traffic. So, but what it needs to look at is the URL. The URL is not in the IPv4 header. It's actually not even in your TCP header. It's in your application level HTTP header, which we'll talk about when we get to it. But so the network, what it has to do is collect the first few packets in your flow, reassemble them, reconstruct your HTTP headers, extract the URL, and say, this is allowed or not allowed. So what the network has to do is it has to piece together some number of packets in order to get at that URL. For that, it needs to know which packets belong to the same user browsing session. And today, the way we do that is through kind of ad hoc heuristics. We say, okay, if these packets have the same source and destination IP address, and they have the same port numbers, and they have the same protocol field, we call that a 5-tuple, then they belong to the same flow. And so I'm going to assemble packets that had that flow. It's a little ad hoc. So for example, if you had one browsing session where you're talking to 2 content providers for that web page, the network gets confused about whether they actually, it has no real easy way of knowing that they're related. So rather than have all these ad hoc rules, what IPv6 is saying is I will allow applications to put a flow label in. And so then the network just has to look at the flow label and say these packets belong to the same user session or the same flow. We'll get back to this when we talk about middle boxes. Any other? Okay, so then moving on, let's look at a quick security analysis of the IP header. So we're going to look at a fairly, as you probably realized by now, the original designers of the internet didn't worry about security. So there are all kinds of things you can do at the network layer that are security threats. What we're going to look at today is one very narrow subset of them, which is imagine that you are a sender and you're sending an IPv4 header packet out, and you get to do whatever you want with the IPv4 header. Okay. What are some of the things that you could do that would be a security problem, that could be deemed as an attack or something? So remember, you get to fill these fields here on this header as you choose. There are many fields that can be exploited. Thoughts? Yeah? So the TTL, and you've actually already done this in section, you could set the TTL to be fairly short so that that's what traceroute does. So then you get an error message back from the router and you're effectively tracing the internal topology of the ISP. Yep. Even easier than that in a way. Maybe not easier, but yep. You could spoof the destination. I was expecting the source, but you can spoof addresses, absolutely right. We can get to a bit whether you're better off spoofing the destination or the source, yeah? You could mess with the checksum so it gets rejected. Interesting. You can certainly do that. Why would you do that? You're only getting your own packets rejected. So it's doable. I would argue that it's not much of an attack if the only effect is that you're dropping your own packets. Any others? Okay, let's go through them. IP address integrity. As someone pointed out, in IPv4 you can put the addresses you want in the source and destination field. Ideally, let's start with the source, which is where more problems arise. Ideally, as a sender, you should be putting your own address as the source field. Right? But if you don't, there's nothing in the network that's actually checking that you are who you claim to be. Right? So you could be sending packets with any source that you want. What are the implications of this? Why would you actually claim to be a source that you're not? Why do you think someone might do this? There's two reasons why you might do it. Yep. Yeah, okay, 3 reasons. You might want to trick the destination. How far would you go with that, though? Because here's what's going to happen. Right, you send a packet, and I claim to be Sarah. And I send a packet to Alex. Alex's response is going to go to Sarah, not to me. Right? So marginal gains there. So the most common reason people do this is, let's say you want to attack a destination. So let's say I want to send tons and tons and tons of packets to Alex and overwhelm his machine and crash it. The minute Alex is under attack, what is he going to do? He's going to tell his ISP, hey, someone's attacking me. You need to put a filter in your network and drop that traffic. The most natural filter you would say is, hey, all these packets coming from Sylvia, she's attacking me, drop all traffic coming from Sylvia. But if I spoof my source address and I choose a different address for every packet, then it's very hard for an ISP to filter traffic because they don't know where it's coming from. Right? All they see is somewhere close to Alex, packets are coming in from millions of different IP addresses, and Alex is being taken down. So this is a very common attack on the internet. And it's hard to know how to filter it if you can spoof addresses. Make sense? There's another one you could do, which is to actually be a pain for the source address that you're spoofing. So this is a different one. So let's say now I want to really annoy Sarah. Right? So what I could do is send packets to 1 million different destinations, claiming that they all come from Sarah. So those 1 million destinations are all going to respond back to Sarah and overwhelm her link. So that's 2 ways in which you can exploit the source IP address. And there are all kinds of attacks people have done, exploiting the fact that you can set whatever source IP address you want. Implications of the type of service field. This one's actually pretty simple. You can just ask for high priority traffic. Right? So your attack traffic is now, not only are you generating attack traffic, it's actually being treated better than other traffic on the internet. If the type of service or getting high priority traffic comes with an extra charge, you have to pay more for your service, then you can combine asking for high priority traffic with spoofing the source address, and you're now passing the bill off to your victim. Right. This is why in practice, as Rob was saying, pretty much all operators, they set or use the type of service field themselves. They don't let end users or end hosts actually set it. Implications of fragmentation, I think we kind of covered this. If you send packets that are too large, that are larger than the MTU, with IPv4 we know that the router has to fragment it, which means the router has additional work to do. So one way to actually attack a router is to send a lot of packets that are larger than the MTU and force the router to do a lot of work. Security IP options as well, I think similar attack. IP options, as Rob mentioned, require additional processing at the router. Often this is done at the control plane of the router, or what we call the slow path. And so again, if you want to try and attack a router, send it packets with a lot of options, and the router, you're using more of the CPU resources at that router. And again, this is the reason why many routers will either ignore packets options, or they'll just altogether drop packets that have options in them. Implications of the TTL, we covered this already. It allows discovery of the topology. This is actually what traceroute exploits. This is arguable. Some of us think traceroute is a great tool that you can use to discover your network topology. Some operators think it's a terrible tool because it allows others to discover their topology. Which side of that argument you come down on, accordingly, operators will configure their routers. If you run traceroute, you'll often see that it doesn't make it, that there are some routers along the way that don't respond. It's because those operators have configured their routers to not respond to TTL exceeded messages. So you can start to see a pattern here of fields that had security vulnerabilities, and operators have responded by disabling them. I could not think of any problem with the protocol field or the checksum field. If you come up with it with an attack, let me know. There's always surprising things. But that aside, I think those were all the security issues I could think that are notable and people have come up with. Any other thoughts on security before I move on? Okay, so with that, recap the IP header design. I hope you feel like it's actually more nuanced than it first seems. It's very easy to look at the IP header and sort of walk through the fields and just say, okay, check, 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 I get it. There's actually a fair amount of careful thought that goes into what is in that header versus not and why. And all of this comes from, you're actually juggling multiple goals. You want an efficient implementation. You want it to be secure. And importantly, you also want to design in some ability to evolve to meet future needs. The IPv4 header did a reasonable job at many of these. I think the IPv6 header does a slightly better job. Security is the one area where there's still clearly a hole. With that, any questions? We are leaving the network layer otherwise. Okay. So with that next topic, we're moving up a layer. We're going to the transport layer in L4. And we're going to start talking first about reliability and how do we implement reliability at that layer. Today's lecture, we're going to cover the basic concepts and mechanisms. The next lecture, we're going to talk about TCP and the protocol details. This is very similar to how we did BGP or how we did routing. We're first going to get the basic concepts. Then we're going to assemble it into a protocol. This material is not on the midterm. Please don't leave the class right away. I will cry or something. So sit through it. It's actually useful for Project 2, and it's going to be critical for understanding TCP. So just, basics. Why do we need reliability? I hope this is pretty obvious to everyone. If you're going to transfer a file on the internet, you want to know you got the file. You got it correctly. You got it in its entirety. Right? So we need reliable transfer. The challenge is how we're going to build this on top of a buggy network or best effort network. And so this is really an exercise in trying to reconcile kind of application abstractions. What is it that application developers want as an abstraction when they're building applications versus what are the abstractions that we can easily support in the network, right? And we've already said we're going to do a best effort. So quick recap of things we've said in the past about reliability. We've said that reliability is the job of the end host, not the network. Right? And we went through this whole exercise with the end-to-end principle that led us to conclude that we want reliability implemented at the end host. We also said that we were going to do reliability at the transport layer, and that's implemented in the operating system. And the argument for why we're doing it there is one of convenience. Otherwise, every application would have to implement what we're about to discuss for the next 2 lectures. Right? How do you actually rebuild reliable transfer on top of an unreliable network? So with that, what are the semantics of correct delivery? At the network layer, we've said the semantics we're shooting for are best effort delivery. Packet may or may not be delivered. What you're going to see is that at the transport layer, the delivery semantics we're going to support are what we call at least once delivery. So at the transport layer, the receiver is going to receive every packet at least once. It might receive the same packet more than once. And you're going to see this is kind of fundamentally the model we have to live with, given a best effort network underneath. And then later, when we get to things like HTTP and the application layer on top of TCP, you're going to get exactly once delivery. So when I reliably transfer file A from point A to point B, at the application layer, it gets to just think that the entire file was delivered exactly once and reliably delivered. The transport layer sitting underneath it is going to see certain packets or bits of that file multiple times, maybe. And it's going to have to learn to deal with that. Okay? So goals for reliable transfer, anytime we start our design, first we talk about the goals. So correctness, which is what we just covered, which is that the destination receives every packet uncorrupted at least once. Okay? That's our correctness goal for the transport layer. What else would we want as goals from a reliable transport? So I'm transferring a bunch of packets or file from point A to point B. I want it correctly transferred. What else do I want? Yeah.
Maybe like arrive in reasonable time.
So timeliness, right? No one wants to sit around waiting forever for the packets to arrive. What else? Efficiency, that's the last one. Okay. I could implement reliability by sending every packet 10 times. That might even be pretty quick. It would probably do the job. It's not a very good use of bandwidth, right, to just say I'm going to consume 10 times more than I need. So we would like to avoid sending packets unnecessarily. One thing to note, our correctness condition said at least once, but there is never a guarantee on the internet that you will for sure reliably transfer a file or reliably deliver a packet. Right? There is always the possibility that the sender cannot reasonably deliver the packet. An extreme example would be if your network is partitioned. You have no path to the destination. Right? So it's totally valid behavior for a reliability protocol to say, I've tried enough, I'm giving up, I could not transfer this packet. The only thing that we ask in that case is that the sender, transport layer, the sender side, has to tell the application, I failed. This transfer failed. And under no circumstance should that transport layer implementation say, I succeeded in delivering the file when it actually failed. So it's okay to fail, but you should know that you failed. So with that, best effort network, just to enumerate all the things that could go wrong. We said packets can be lost. We said they could be corrupted. They can be reordered. In case you've forgotten, let's say I was sending packet 1 and followed by packet 2, and then I had a route change, and packet 2 actually got to take a path that was faster than the one packet 1 was taking. So it's acceptable for packet 2 to arrive before packet 1 at the receiver. Packets can be delayed. We've talked about queues, packets sitting in queues and incurring queuing delay, and packets can be duplicated. So it is actually possible for the network to generate an unnecessary copy of a packet, and we'll get to that in a minute. These are all the things that can go wrong. These are all the things that our reliability protocol is going to have to fix. Okay, so the way we're going to talk about as we develop the protocol, just a quick reminder of these kinds of diagrams where we have time going down, and we send packets from a sender to a receiver. They're going down in time and coming back to the receiver. Half of that is the one-way delay from sender to receiver. The time for the packet to go and come, some kind of response to come back to the sender, is what we call the round-trip time, or the RTT. Okay, we're going to be using this as we go. Yep. Not in what we're doing. So we would say it's the time from when the last bit went left to when the first bit came. But we're also not doing these kind of microscopic calculations in here. Yep.
Would the one-way delay be different, like coming into the don't know if they'll take the same path back?
Yes, it could. So there's no reason why your one-way delay has to be exactly half your round-trip time. In all the examples we'll be doing here, yes. But on the internet, end-to-end, no, you're right. And we talked about this with BGP, that paths could be asymmetric, for example. Any other questions? Okay, so let's get started designing a reliability protocol. And we're going to start with a single packet. This is very simple, but it actually highlights most of the building blocks we're going to need. So let's step through it fairly slowly. So remember, these are all the bad things that can happen to a packet. And we're going to say we have a sender here that's trying to send a packet to the receiver. And the packet gets dropped. Okay, the packet got lost. What should the sender do? We've seen this already in a different context. Yeah, set a timer, right? So the sender is going to start a timer when it sends the packet. After some amount of time, if it's not heard anything back from the receiver, it's going to time out, or the timer will expire, and it's going to resend the packet. It's going to keep doing this. So the receiver, when it receives the packet, is going to send back what we call an acknowledgement, saying, I got the packet. When the acknowledgement reaches the sender is going to cancel its timer. Okay? This is kind of the very basic mechanism. Are we good with this? Yeah? What if the ACK got dropped? Do I need to do anything more than that? No, right? I just had a timer, I timed out, I sent the packet over, and this time it made it through, the ACK comes back, the sender is happy. So we reliably delivered the packet, but notice the receiver received the packet twice. This is fundamental. Can you think of a way we could have avoided having the receiver see the packet twice? You actually can't, because there's no way for the sender to be able to distinguish between the packet was lost versus the ACK was lost. So the sender has to retransmit. The receiver is going to see it twice. This is not going to worry us. This is correct. By our goals of at least once delivery, we got it there at least once. We got it twice, but that's fine. Okay? This brings up the question of how do we set timers. Right? If your timer is too long, you're going to delay delivery. Right? You're going to wait too long to retransmit. If your timer is too short, you're going to unnecessarily send multiple packets when you didn't need to. Ideally, what kind of timer do we want? Order what time scale? What roughly would be a good timeout value? Yep. The same as your RTT. So ideally, your timeout should be proportional to your round trip time. In practice, this is actually not trivial to get right, and we're going to talk about this when we talk about how TCP does this, because your round trip time can be anywhere from 10 microseconds to hundreds of milliseconds. So you have many orders of magnitude differences in your path. Right? So if you set it wrong, you could be 10,000 times slower than you need it to be, for example. So we're going to have to learn that RTT. Also, it varies in time, depending on what the load on the network was, whether your packet was in a queue or not, for how long it was in the queue, and so on. So actually estimating a good timeout is a non-trivial question. In practice, your timeout is what you would, if all else has failed, then you will take a timeout. But you're never happy to actually have a timeout. We're going to try and work pretty hard to not have to rely on timeouts. But so with that, we now know how to deal with packets or ACKs that get lost. Okay? How about packets that get corrupted? So now I sent this packet along, a few bits got flipped along the way. What are we going to do to deal with that? Again, we've seen the mechanism for this before. Yep. So we had this checksum. So we're now going to compute a checksum at the destination, make sure that it matches what the packet sent. This is not the same as the IPv4 header checksum. Remember, that checksum was just over the header. We now need a checksum over the entire contents of the packet. Right? We're checking whether the file was actually correctly transferred. So we're going to need a checksum that covers the payload. If the checksum fails, you could send back feedback to the sender saying, this is a negative acknowledgement. You sent me a bad packet. We call that a NAC for negative acknowledgement. And then the sender can resend the packet. Assuming it made it through this time, you would correctly transfer. Okay? Is there something else you could have done instead of sending a NAC? Yeah, just do nothing. Just drop the packet. And exactly the same mechanism we talked about with timeouts will work. So if you believe that bit errors corruption is very, very rare and you don't want the additional mechanism, it's totally fine to not have NACs. Just don't bother doing it. And TCP, in fact, doesn't have negative acknowledgements. So with that, we now know how to deal with packets that can be lost or corrupted. What about packets that get delayed? So let's say this packet here gets delayed, makes it on its way to this receiver, checksum worked out, you got back an ACK. Is there any problem? Not necessarily, right? If your packet was delayed but got there before your timeout, you're just fine. If it got there after your timeout, what would you do? The sender will send a duplicate. The receiver will send a duplicate, another ACK. So we now got both two packets. The packet was delivered twice at the receiver and the ACK was delivered twice at the sender. But it's not the end of the world. This is still a correct delivery of the packet. Okay? So we're good. We don't need any new mechanisms to deal with delayed packets. If you walk through the same but reason about delayed ACKs, you'll see that we're still fine. So we can also deal with delayed packets. What about if packets are duplicated? So what does a duplicated packet mean here? It means that the network somehow generated a duplicate packet and sent it. It sent a copy of the packet to the destination. Your first thought, really the only thing that's interesting about this case is why would this even happen? This is very, very rare, but it has been seen to happen on the internet. And it's usually because you have some kind of link technology that is doing reliability at that link. And so at that link, one end, the sending side of that link, decided to retransmit a packet because it thought the other end didn't get it. So it retransmitted the packet. And then the receiving end of that link forgot, or it had deleted the state that told it that it had already forwarded that packet, and so it sends it twice. So it's really this corner case, very, very few occurrences of anyone ever seeing it, but actually Vern Paxson, who was on the faculty here, was the first to actually publish that this was a thing that happened. And he went to the router vendors and said, your router is, your link technology is duplicating packets, and they were like, no way, it doesn't happen. And then he was like, I can show you that it happened, and after much back and forth, he actually convinced them that they had a bug in their implementation and this could happen. So rare, but happens. From our point of view, let's not worry about how it happens. If it happens, what do we do in terms of reliability? Is this something we have to worry about? No, exactly. You got a duplicate, you sent another ACK, the sender got two ACKs. The sender was already prepared to deal with that. Okay, so we're good. So with that, we actually know how to deal with all the things that can happen when you have a single packet case. We don't have to worry about reordering just yet because we're only talking about a single packet case. Okay. So we now know how to reliably transfer one packet across the internet. It's a very simple algorithm. Sender sends a packet, sets a timer. If it doesn't receive an ACK in time, it resends the packet, resets the timer. Receiver, very simple. You get a packet, you send an ACK. Okay? Any questions on this? This should be really simple. Okay, so what have we learned? What we have learned actually are the building blocks for a solution. We now know about checksums, feedback, either positive or negative ACKs, retransmissions at the sender, and setting timers that when they fire, we're going to retransmit. We also have in place semantics of a solution, right? That both the sender and the receiver could see more than once delivery. So, if there are no questions, I'm going to move on to sending multiple packets. So now we're going to talk about sending multiple packets. The only design component we actually have to add to the ones we had is the notion of sequence numbers. Okay. So now we're going to say that data packets carry a sequence number, and the ACK tells you what sequence number it's ACKing. Okay. So like here you have packet 1, and then you have ACK 1, then you send 2, and you're ACKing 2. That's really the only mechanism we absolutely require. So with that, we have all the necessary building blocks to actually build a reliable protocol on the internet. The straw man that all the textbooks will discuss, and somewhat surprisingly, some people actually use this in practice, wouldn't advise it necessarily, definitely not on the internet, is what we call a stop and wait protocol. Okay, and the stop and wait protocol is as simple as can be. It uses the single packet solution we just delivered. It says you wait for packet I to be acknowledged before you send the next packet I plus 1. This is actually a correct, reliable delivery protocol. It's also an extremely inefficient one. You're sending one packet every round trip time, in the best case. Okay. So if you look at it visually, this is what we're doing. Okay. Send packet 1, wait for the ACK. When I was waiting for ACK 3 and I didn't receive it, I took a timeout, resent it, and only after I got ACK 3, I sent packet 4. This is actually a reasonable protocol if your round-trip times are really, really tiny. So sometimes inside a machine, you will see different components on a server doing something like stop and wait. But across the internet where you have hundreds of milliseconds round trip times, this is not something we want to do. So what would you do to make this go fast? Standard trick in computer science. Yep. Yeah, so parallelism, right, or pipelining. Just send multiple packets out at the same time. We call this having multiple packets in flight. What does that mean? That the sender sent out multiple, it's okay to transmit lots of packets that have not yet been acknowledged. So you can have multiple packets in flight that are waiting to be acknowledged. Okay. And so now things start to get a little bit more interesting. So this is what we call window-based algorithms. The basic idea is we're going to tell the sender you can send up to W, some parameter W, number of packets in flight at any time. W is what we call the size of the window. Okay. And so a simple algorithm, just extending what we did so far, was to say the sender can now send W packets, and when it gets one ACK back, it's going to send the next packet in line. Okay, so what does that look like? Let's say here we had a window of 4. So the sender got to send packets 1 to 4, and now it's waiting. Okay. So its window at this point is 1, 2, 3, and 4. These are the packets in flight. Again, packets that have been sent but not acknowledged. When the sender gets back ACK1, it's now okay to send 5. So now its window is 2 to 5. So we call this sliding the window forward. When you get the ACK for 2, you slide the window one more time, and you're allowed to send 6. Okay? So at this point in time, your window is packet numbers 3 to 6. These are packets, W packets that you were allowed to send. You're waiting for ACKs. Everyone good with this? Yeah. Okay, so going back to, we said we had all the necessary building blocks. In practice, we have this one more parameter or mechanism, that's the window and the window size. We do this for efficiency, not for correctness. The stop and wait protocol we had was correct. It would correctly deliver packets. This is all about performance and optimizing for efficiency at this point. But once you have windows, there are a lot of design questions that open up. First is just, what is that window size? Right? How many in-flight packets do you want? The second is the nature of the feedback, because if you think about it now, the receiver is sending all of these ACKs one after the other back to the sender. Could it be sending more useful information than simply, I received packet 3? It could be sending you something about the history of the packets it's received. You could then use that to detect loss, right? As we're going to see, depending on which ACKs you get, it's a pretty good indicator of which packets the receiver did not receive. So maybe we can do better than waiting for timeouts. And finally, how do you respond to loss as you start seeing these ACKs come in? So this is going to set up the kind of the questions that form what we call a window-based reliable protocol. Let's start with the first question. How big should the window be? Thoughts? How big a window do you want? What are the considerations we have to worry about? Yep. The bandwidth of the link, right? So you want to take advantage of network capacity, this notion of filling the pipe, send as many packets as you can. At the same time, what should you worry about maybe? Yep. The MTU of your network. Yes, I wouldn't have said so much for reliability because, say more, because if you send something more than the MTU, the network will fragment it and send it out, which the fragments will still arrive at the destination. So remember that now we are up at the TCP layer, at the transport layer. So all the reassembling of fragments and all of that has been done by your layer 3 implementation at either at the receiver. So you're at your transport layer, you're now receiving the full packet. So we actually don't have to worry about fragmentation at this layer. Yep.
Question. So how would a router prioritize trying to send out 2 files at a write at the same time? Does it send out the first file first
So remember, the router is just getting packets, right? And so if your question is between two packets, one of them needs to be fragmented, the other not, is that? So your router is not seeing files, it's just seeing packets, and it's just taking one packet at a time and sending it out. And we could be doing more fancy scheduling, but for most of this, certainly for this discussion, we're saying that routers are just doing FIFO order scheduling. So whatever order the packets come in, I'm going to send them out. Yep.
Question about citing window. If you receive an act from two but not from one, what do you do?
We're going to get to that. Hold on to that question. Okay, so other things you should worry about in terms of picking your window. You want to make full use of the pipe you have, but you also don't want to overload links. Right? Because if you overload links, you're going to end up with dropped packets. Not a good idea. So this is a problem we call congestion control. And the other concern, which we haven't yet touched on, but we're going to start to worry about, is you also don't want to overload the receiver. Right? Because the receiver can only pick up packets at some rate, has a certain amount of buffer space, so you don't want to overload the receiver. We call this flow control. For this lecture, and until we get to congestion control, ignore the second two concerns. They are concerns. We'll deal with them when we get to congestion control. So for this lecture, just say that we're focusing on the first goal, which is we want to fill the pipe, right? And if we want to fill the pipe and fully use network capacity, what does that mean in terms of the sender behavior that we're looking for? What it means is we want the sender to always be sending for the entire round trip time. We want the sender to be busy transmitting. Okay? So for an entire round trip time, I want the sender to be busy. What that means is that when an ACK comes in, the sender should pick up the ACK and send out another packet. Let's look at that visually. I think it's much more intuitive when you look at it in terms of an example. So we said in this case your window was 4. And the sender had sent 4 packets, got these 4 ACKs. Your round trip time in this case is the time it took you for the packet to get to the receiver and the ACK to come back. If you notice, there was a large fraction of that time that the sender was just sitting there, doing nothing, right, waiting for that ACK to come back. Because your window was too small in this case. 4 packets was not enough to keep the sender busy. What we would have liked, ideally, is that the sender is always busy sending out a packet, and it had a larger window that allowed it to keep sending for the duration of the round trip time. Okay, so what does this mean? When we think about it more rigorously, what we're saying is, let's say that B is the minimum bandwidth of a link along the path. It's what we call the bottleneck bandwidth. Okay. So there's no case in which the sender can be sending faster than the bottleneck bandwidth. Right? That's as fast as it could send. But you also, under the assumptions we've made, we don't want the sender to be any slower than that bottleneck rate, because otherwise you're wasting capacity. And so what that means is that for this setup, we want the sender to be sending at the rate B, this is the bottleneck rate, for the entire duration of the round trip time. Okay. So this gives us our condition that we want window size, the W parameter, to be set such that the window size, which is how many packets you can send, times the packet size, let's assume a constant packet size here, is the round trip times delay times the bottleneck bandwidth. Is this making sense? Let's look at it visually, because we all trip on this. So in this case, what I'm showing you here is one link, but I'm showing it to you in a bidirectional. I've split up the path going from the sender to the receiver and coming back from the receiver to the sender. Because remember, a link is bidirectional. Right? I can send B bits per second and I can receive B bits per second at the same time. So in this case, I'm saying my window at the sender should be 6 packets. Right? And if you look at the pipe, I have 3 packets on their way to the receiver, and I have 3 ACKs coming back to the sender. So there's 6 packets that the sender has sent, but they're not acknowledged yet. So everyone, the thing that confuses people is they look at the pipe and they say, it can only hold 3 packets. Why isn't my window size 3? Right? But if you think about it, if we'd said the window size was 3, what is the sender doing while it's waiting for the ACKs for those 3 packets to come back? It's not doing anything. So if we really want what we call an ACK clocking behavior, where every time I get an ACK, I put a packet in, then I need my window size to be the round trip time, the delay going to the receiver and coming back, times that bandwidth. Any questions on this? Is it clear? Yeah? Okay. So that's the window size. We're going to try and set the window size based on the round trip delay. So now let's talk about what we can do in terms of design options now that we have multiple or W packets in flight. So what we've been talking about so long, all this time, is what we call individual packet ACKs, which is when the receiver gets packet I, it sends back an ACK saying ACK I, meaning I received packet I. If you look at this in the context of a window, you'd realize this, we could be doing better. So here's an example where I sent 4 packets, all 4 of them made it, but ACK 2 was dropped. With the protocol we've been designing so far, what would the sender do? It would take a timeout on packet 2, because it never received the ACK, and it would resend it. But packet 2 was actually received at the receiver. And the receiver sent me 2 other ACKs, or a bunch of ACKs after that. Right? So this should tell you that you could put something into the ACKs that would allow the sender to kind of tolerate the loss of an ACK, to figure out that packet 2 had reached even later. Thoughts? What would you do? You get to redesign ACKs now. A new type of ACK. Yep. I'm going to take that and flip it around. You're getting there. What you could do is something we call full information ACK, which is when I send an ACK, I tell the sender all the packets I have received so far. Because why should I only tell you about one packet? I can tell you about all the packets I've gotten so far. Right? So the way this would work is you would give the highest cumulative ACK, which means that you've received all packets up to that sequence number, and then any additional packets that you received. So something like I got everything up to sequence number 12, and then I received packets 14 and 15. What would that look like here? So with cumulative ACKs, your ACKs would now look like what you have there on the right-hand side. Right? You'd be saying, I got everything up to 1, everything up to 2, everything up to 3, up to 4. So in this case, trivially, the minute the sender received the ACK for packet number 3 or the ACK for packet number 4, it also knows that you received 2, and so it doesn't have to retransmit 2. Clear? This was a pretty case. It doesn't always look this pretty. Let's say that in this case, you lost every other packet. So you lost packet 2, you lost packet 4. So what do your ACKs start to look like in this case? So when you got packet 1, you said, I got everything up to packet 1. But then the ACK when you got packet 3 says, I got everything up to 1, and I got 3. When you got packet 5, you say, I got everything up to 1, I got packet 3, and I got packet 5. Right? So you can see that the information you're starting to put into your ACK is not scaling so well. Right? It's starting to get kind of long. Is this making sense to everyone? Yeah. So we like full ACKs, full information ACKs, because they tell the sender exactly what's going on at the receiver. There's no guesswork. But the problem with them is they don't scale very well. There's too much information in there. In the worst case, you could have as many, the size of your full information ACK could be on the order of your window size, which can be tens of thousands of packets in practice. So that brings us to our last type of ACK, which is kind of trying to achieve a sweet spot between the first two. It's what we call cumulative ACKs, which is saying, I'm going to take the idea from full information ACKs of telling you what's the highest sequence number I've received, such that I got all packets before that sequence number. But it's going to drop that trailing edge of which other packets have you, out of order packets have you received. Okay, so it's just the highest sequence number for which all previous packets have been received. Any questions on what cumulative ACKs means? All right, so let's see them in action. So in this, going back to that example here where ACK 2 was lost. So in this case, the cumulative ACKs interestingly look exactly like the full information ACKs. And that's actually not surprising because we didn't lose any data packets. So the ACK is just telling me I got everything up to the packet number 2, up to 3, up to 4. And so in this case, cumulative ACKs behaves exactly the same as full information ACKs. The minute you get the ACK for packet 3, you know that it also received 2. The sender is not going to retransmit 2. In the case where I lost every other packet, like packet 2 and packet 4 in this case, this is where you start to see a difference between cumulative acts and full information acts. Right? Because in every case here, the receiver is just saying, I got all packets up to 1. Right? So cumulative acts, it scales better than full information acts, but it can be ambiguous about exactly what the destination received. We've lost some information there. And as you are going to see when we start designing TCP, TCP uses cumulative acts, and TCP tries to guess what the receiver has seen. And so things get a little tricky. There is one thing to note, though, that every time you get one of these acts, you are learning something about the receiver. You're learning that the receiver received some packet. You're just not learning exactly which one it received. Let me recap the act trade-offs, and then let's pause to see the question. So individual acts, this is when I get packet I say ACK I. It's very simple. It's very compact. The problem is if you lose an ACK, you will always have to retransmit that packet. You would always have to take a timeout and retransmit. And remember, we don't like timeouts. Okay. With full information acts, suppose you have all the information you want. There's no ambiguity. You're completely resilient to ACK losses. The problem is it takes a lot of overhead in the ACK packet to actually enumerate all these packets. And so cumulative acts, they are compact. They are as compact as individual acts. They are more resilient to ACK loss. So as you saw when that ACK was being lost, cumulative acts recovered from it. But it is incomplete information on which data packets were actually received. You have a good indicator of how many packets were received, but not exactly which ones. Any questions on this? Let me pause here. Yep.
How is this so you can, like, how is cumulative useful if you can't know which packets you actually did?
Well, so for example, in the case where you had the ACK loss, right? If I had individual acts, I was retransmitting packet 2 here because I never received any information about packet 2. But here, when I get the cumulative ACK for packet 3, it's telling me I got everything up to packet 3. So the sender knows not to resend packet number 2. Right. So for the next case, you're right. It doesn't know. And this is going to come back to trouble us. But it does tell us something, which is the presence of an ACK tells me that a new packet was received. So I know how many packets were received. I don't know which ones. If you're feeling like, I don't like cumulative acts, I agree with you. But those are the trade-offs that come with it, yeah. Yeah, so I think the question is, why don't we do a better job of trying to scale full information acts and say that I'm going to give you full information on some piece of it? Is that yes, and so that is something, it's approaching something called selective acknowledgements that TCP uses. The reason we talk about cumulative acts is TCP uses cumulative acts because they were really concerned about keeping acts small. Over time, there's been this new extension, SAC, or selective acknowledgement, that we'll also cover. But yes, you're absolutely on the right track. I think the question's all, there's a spectrum between cumulative and full information, and it's an interesting design point. Yeah? Why wouldn't you send which ones you didn't? Well, you could. It's a reasonable design to consider. I would have to actually walk through the case, but here would be my intuition, would be when I tell you which packets I received, that's correct information. When I tell you which packets I didn't receive, it might just be delayed and coming in. So if I tell you I didn't receive 2 and then I receive 2 right after I send that, the sender is going to retransmit 2, if you believe the information. Any other questions on ACK types? Okay. So we use these ACK types. Some of them is, they're what is used in protocol. Some of them is also just to show you the design space. It's not the only kinds of ACKs you could come up with, for sure, but these are the ones we're running with and sort of analyzing. So with that, what do these ACK options mean for detecting loss, right? So far we've been saying that the way you detect loss is that you have a timer that expires. So if the packet time it times out, you assume it's lost and you resend. But now that we have all these acts coming in, as you've already started figuring out, you can actually look at the acts that you're receiving and use that to decide whether you think something is lost. Okay, so a reasonable rule is to say, I'm going to look when I receive k subsequent acts after the packet I was expecting. So I was expecting a particular packet ACK, and if I didn't get it, but I got k subsequent ACKs for other packets, then maybe I can decide that that packet is actually lost. Right? So as an example, let's say that only packet 5 was lost. So at the sender, I had sent a whole bunch of packets, and I've received ACKs up to 4, and I'm expecting 5. I'm expecting an ACK for 5. Right? And I haven't received an ACK for 5, but now I receive an ACK for 6. So when I receive the ACK for 6, you could think, well, okay, maybe there was a little bit of reordering, maybe the ACK for 5 was delayed, so I'm going to hold on. When you receive the ACK for 7, you feel like, okay, that makes 2 ACKs I got that were beyond what I expected. Maybe packet 5 or ACK 5 was really lost. And so you can go on that way, and you have some number of k, which is after you've gotten k subsequent ACKs, you decide, okay, the packet I was expecting is lost. I'm going to treat it as lost. Yeah? It depends which ACK mechanism we're using. So you're right, it'll be a little different depending on what type of ACK we're using. But I will receive an ACK for that packet. What I mean by that is that data packet 6 arrived. It caused the receiver to send me some ACK, and that I'm receiving an ACK corresponding to packet 6. It's not necessarily an ACK that's telling me this is packet 6 was received. And we're going to do that in just a second. Right? So exactly how this looks depends on the ACKs you're using. So let's actually walk through this. Right? So let's say we had individual ACKs, and only packet 5 was lost. If you look at the stream of acknowledgements that the sender is receiving now, right? This is individual ACKs. So I receive packet I, I send ACK I. You're going to see a stream of ACKs that look like this. As you can see, we never got an ACK for packet 5. So after we've said k subsequent ACKs, so in this case, let's say it's 3. So after I've gotten an acknowledgement for packet 6, 7, and 8, the sender is going to say, by this rule, it's going to say packet 5 is lost. Okay? So we're going to treat this as equivalent to a timeout. At this point, we've decided packet 5 is gone. Yeah? With full information, it's exactly the same story, except that it's even more explicit where the hole is, because the ACKs you're getting from the sender are going to tell you, I got up to 4 and then I got 6, and so on. And when you receive that you got up to 4 and 6, 7, 8, you can see that the receiver received 3 packets beyond 5. And so you can declare by this rule that packet 5 is lost. Yep. What about with cumulative ACKs? And this is where cumulative ACKs come back to bug us a bit. Right? So what your ACKs would look like in this case is when you had packet 6 arrive at the receiver, it sent back an ACK saying, I received all packets up to 4. Okay, so we call these duplicate ACKs because they're saying the same thing as when we received packet 4, when we got the first ACK for packet 4. Okay? And so the same rule in this case with cumulative ACKs says, after we get 3 duplicate ACKs, or dup ACKs is what we call them, then we say that packet 5 is lost. Yeah? As someone already pointed out, there's a hitch here with cumulative ACKs, right? I got 3 duplicate ACKs. It tells me that the receiver received 3 packets, but I don't know which packets these are. I don't know that it was 6, 7, and 8. It could have been 7, 8, and 9, for all I know. Okay, we don't know. We're going to have to deal with this. Any questions on this? So this is just using the extra ACKs we're getting in to declare a packet as being lost or not. Okay, so what we're going to do with this is now decide when we make this decision that a packet was lost, how do we respond to it? Okay? The thing we want to do is resend the packet that was that we believe was lost. But as we'll see, this can be a little tricky. So let's walk through that. So response to loss, so far we've said on timeout, always retransmit the corresponding packet. Okay. What about when ACK-based rule fires? Okay. So what we've seen so far is that when we have this, so 3 subsequent packets that have been ACKed event occur, you will retransmit the packet that you think is missing. Right? With individual ACKs or with full information ACKs, which packet you should retransmit is very clear. The whole is very clear in the stream of ACKs that you got. With cumulative ACKs, if you have a single packet loss, it's very clear. But what we're going to see is that when you have multiple packet losses, it's sometimes not clear. I have a detailed example in the backup that we'll walk through if we have the time. But otherwise, I hope you can see the intuition here, which is I received duplicate ACKs, but I didn't actually know which packets were received at the receiver. And so I'm going to have to guess when I retransmit a packet. Okay. So the response with cumulative ACKs issue, they don't tell the sender exactly which packets were received. They do tell you how many packets were received. That's the number of duplicate ACKs, not which ones to resend. And so that leads to some amount of guesswork around which one you should retransmit. And when we do TCP, we'll talk about how TCP does this in detail. Okay. Let's come back to this if people want to actually walk through the example. But for now, let's back up a level first and just taking stock of what we've done in terms of design building blocks. We have all of the design building blocks that we need to implement a reliable transport protocol. Checksums, ACKs, NACKs, timeouts, retransmissions, sequence numbers, and windows. There are trade-offs in how you apply them, whether you have cumulative ACKs versus full information and so on. But what you can do now is take all of those design options and design a reliability protocol. Okay, we've seen one, stop and wait. That was the one packet at a time. There's another very simple variant called go back n that you'll see in section. It's another one of these canonical examples, not very useful in practice. TCP is the one we will do in depth next time. But I think it's more important that you can reason about how to design a good reliability protocol from these building blocks, because in fact, as you'll see, TCP is not a perfect protocol in how it combines these building blocks. It's starting with the fact that it does cumulative ACKs. So we can do better, and we'll do better. Just a quick preview of what TCP does. It actually uses all of these building blocks, most of them that we've covered. It does use checksums, uses ACKs, no NACKs, it has windows, sequence numbers, cumulative ACKs, and it counts the number of duplicate ACKs. It does optionally have this option for a form of full information ACKs that we call selective acknowledgements, so we'll cover that as well. And then it has these timer estimation algorithms. Let me jump, I'm going to skip this for today. Let me jump to an example of ambiguity with cumulative ACKs. How many of you feel like you want to see the example? All right. So let's see where the issue comes from. So let's first look at responses with individual ACKs. Okay? The example we're going to consider here is a sender that has a window size of 6. And we're using a value of k equal to 3, meaning when I get 3 subsequent ACKs, not the packet I expected, I'm going to declare the packet as lost. Okay? So in this example, packets 1 and 2 have been sent and ACKed. 3 to 8 are in flight. So what I'm showing you here with these numbers are the sender's view of the window. Okay? Red are the packets that it has sent, but they've not yet been acknowledged. And you can have up to 6 of them, because that's your window size. And now let's say that you had 2 packets that were dropped, 3 and 5. Okay? So now what happens at the sender? When ACK 4 arrives, right, what is the sender going to do? It's going to say, okay, packet 4 was delivered, I have a window size of 6, so I can now send packet number 9. When ACK 6 arrives, it says, okay, packet 6 arrived. I'm allowed to have 6 in-flight packets, so I'm going to send out 10. Are we good with that? Now when the 7th ACK arrives, this is the 3rd subsequent ACK. So the sender is going to say, okay, packet 3 is lost, because I've gotten 3 acknowledgements after 3 without receiving 3. So packet 3 is gone, so that means I can resend 3. Plus I received an ACK for 7, so I can send 1 more packet, so I can send 11. Is everyone good with this step? Yep.
There's not a blue window on the packet sequence. It's a window on the queue of packets.
It's a window in the sense of how many outstanding packets can you have. Yeah. Are you good with that? So when we do TCP, we'll do the actual how you maintain the variables and what range of windows you can have outstanding. But for now, it's 6 packets in flight. Yeah. So what happens when ACK8 arrives? So at this point, you've gotten 3 subsequent acknowledgements for packet 5, right? You've gotten the ACK for 6, for 7, and for 8. So you're going to declare at this point packet 5 is lost. So you're going to resend 5, and you get to send 12. Is everyone comfortable with why I get to send 2 packets? Yeah. Okay, great. And then when 9 arrives, you continue. You send 13 and so on. So this is pretty clean. If I did the same example with full information ACKs, it would look exactly the same because you're getting the same information. Okay, so we're going to skip it, but walk through it in your heads. So now let's walk through this with cumulative ACKs. Okay. So when you get the ACK corresponding to packet 4, what you receive at the sender is something that says, I'm acknowledging 2. Okay. So this is our first duplicate ACK. But I did get 1 packet out of the network, so I get to send 1 more, so I send 9. When I get the ACK for packet 6, it is still saying acknowledgement 2. The number of duplicate ACKs I now have is 2. Okay? So I'm going to send 10. Everyone good with it so far? Right. When I get the acknowledgement corresponding to packet number 7 now, so at this point I have 3 duplicate ACKs. So this is the point at which I decide packet 3 is lost. And it's clear which one is lost, right? Because I've gotten everything up to 2. The reason that number is not going up is because 3 is lost. So I'm going to resend 3 and send 11, similar to individual ACKs. Are we good so far? Yeah. So where the trouble occurs is when you get the next ACK2. So when corresponding to packet 8 being received, you get yet another ACK2. And at this point, you have 4 duplicate ACKs, so you know that there's a packet that got 3 subsequent ACKs. You know that since a packet was received, you're allowed to send 12. But which packet should you resend? You have no way of knowing whether you should resend 4 or you should resend 5 or some other packet. Is this making sense? Okay, and so when we talk about TCP, we'll talk about how TCP addresses this, but this is the problem that is being addressed. And since I have 2 minutes more, let me go back in time and cover one other thing. So everything we've been talking about so far is reliability based on this notion of I'm going to send a packet, wait for acknowledgements, send another packet. So it's ACK based. Any other thoughts on how else could you do reliability? If I didn't want to do this per packet accounting or just a completely different design approach. Clear your heads of everything we've talked about this. Yep. You're on the right track. So you could just send packets, keep sending packets until the receiver tells you, I got everything, stop. And you mean keep sending the same packets over and over. Could you do better than that? So if I had 10 packets to send, I could just keep sending 1 to 10, 1 to 10, 1 to 10 until the receiver tells me I got all 10. Valid. It's a totally valid reliability protocol. It's not very efficient.
Would you implement like another protocol? Like, okay, so don't receive like an acknowledgement for 3. The sender like probe and be like, hey, did you receive this packet and ask for an acknowledgement?
So have the receiver tell you which packets it wants.
Yeah.
Yes, that would be a little bit of a pull-based. We're kind of using ACKs to do that. Right. For those of you who've maybe taken some EE courses, what we could do is use coding theory, and there is a large amount of work in this space, which is you take the data and you encode it to be resilient to loss. So the way this works is you take, say, k packets, you encode them as some number of packets n larger than k. So let's say you took 4 packets and you could encode it as 7 packets. And these codes have a property where it says You took 4 packets and you encoded them as 7 packets. If you receive any 5 of these packets, I'm making up numbers, but if you received any 5 of these packets, you would be able to reconstruct those 4 packets. So there is this entire literature on different coding schemes you can use that would allow you to tolerate some amount of loss, but still not, send every packet 10 times. So you could just keep sending packets with some amount of redundancy built into the packet. And you can reconstruct the original packets from the encoded streams. So there's a whole literature on codes that have very different efficiency trade-offs. We don't cover them in this class. I just wanted you to know that coding theory and coding packets is a reasonable approach to doing reliability. It's not commonly used on the internet. Some of the video streaming protocols have used this at the application layer, but it's not made it to one of the internet's transport layer protocols. But it is an option if you wanted to do a slightly different form of reliability. The benefit here is that you don't have this back and forth on acknowledgements. You can just send a stream of packets, and it's tolerant to a certain level of loss. So with that, any questions? Okay, thanks. Next lecture is a review lecture, midterm review lecture. Thank you. Oh shoot, this was off the entire time.